So our next presentation is going to be coming from Shiv Meka, at the WA Department of Health Data Science. He's going to be presenting Convergence of AI and HPC to transform patient care. Shiv, how are you? I know you're using Mark's setup.
Thanks for the invite, Brian and Mark. Can you all hear me?
I can hear you. I can see you.
Yes. I'm just trying to open my PowerPoint. Hi guys. I'll be talking about how AI and HPC together help with improving patient care. And some of the examples that I'll give today are based on real projects that we have implemented here in WA Health. But first off, so WA's health system, or Western Australia Department of Health, we have around 80 hospitals and then almost like 50K daily admissions, and half of them are emergency and the others are elective. And we are in the Perth metropolitan area. And as you see, we are from the land of quokkas, the most happiest animal. And that's what Posy used for its supercomputer. And we extensively use Posy for a lot of our HPC and AI workloads. We're just 8 kilometers away. And not just us, there's also Royal Melbourne Hospital as well as Alfred in Melbourne as well, running their workloads on Posy for their own health needs. So you see that little circle there? That's where we're located. And you also see a helicopter right next to us. And so the building always shakes when there's a landing. But first, a small video about what Hive is.
Hi, it's Katie from AMU. I've just received a Hive alert for Lawrence Brooks. Can you come and review him? I understand that you're an ED. All right, great. Thanks, mate. Hi, Lawrence. You look really uncomfortable and short of breath. Are you in pain? Okay, so what we're going to do is contact the Hive team on the video. You met them this morning. Are you happy with that? Okay, just contacting them now, and let's get you back to bed. Can you swing your legs over for us?
Hi, Lawrence, Katie. It's Eliza calling from the Hive. We've just received an early warning alert for Lawrence. It says he's having runs of AF at 120 beats per minute and desaturating down to about 88%. Lawrence, are you happy if we continue this consult?
Morning, Eliza. Lawrence already consented to the video call. As you can tell from the briefing a few hours ago, he's feeling more unwell. So Lawrence, what Eliza is saying is that your heart rate is going quite fast and in an odd rhythm, okay? And you're very short of breath. So we're concerned that you have some fluid on your lungs, and that's creating some stress with your heart and your lungs. So what we can do is get some medication, and to treat the heart rate and the fluid on the lungs, we're just going to get some more advice from the medical team, okay?
Yeah, Lawrence, you don't look too comfortable. Katie, have you been in touch with the team on the ward?
Yes, Eliza. So I spoke to them about 5 minutes ago. They're just in the emergency department now, but they're coming.
Okay, thanks, Katie. Lawrence, I'm glad your doctors are on the way, but I think what we'll do in the meantime is I'll have a chat with the Hive doctors and we'll see if there's anything we can get started from up here.
Thanks, Eliza, for escalating to the Hive doctor. I'm just putting him on some oxygen via the Hudson mask now, and hopefully that will increase his saturations.
Lawrence, is your shortness of breath improving? Fantastic. Katie, I think we should do a 12-lead ECG as well, just so the doctors have some fresh information when they do arrive.
Yeah, sure. I'll do that ECG now. Lawrence, what that means is it's a tracing of your heart from outside, and we'll give it to the medical team, and they can have a look at it when they come and review you. Thanks, Eliza, for your help. I think we're okay here, but I'll let you know if anything changes.
Fantastic. Let's aim to speak again at around 6 p.m. Call anytime before if you need. Bye for now.
If you look at the video, there's a lot of monitors, a lot of wires and leads, and a lot of medical jargon. So this was some time back when the system was kind of reactive. So it's after an event happens that the clinicians attend to the emergency or whatever the health state is. But you see here, so a clinician gets to monitor multiple patients at the same time. On the right, you see these clinician consoles. So they are clinicians on call 24 hours a day. And sometimes we also monitor for people in the States, especially during our nights and during our day and during their nights, and they cover for us. And what you see on the left is what is called a patient flow monitor that tells us what the state of each ward across the hospital is. But this was back then. This is when you're kind of reactive. You're reacting to situations or when there's derangements of vitals. But what we have now are a couple of machine learning assisted technologies. So if you see a POSI icon, those are the models that are trained on POSI. But we use a range of models. So when you get admitted to like ED or emergency or ICU or in Royal Perth, you're exposed to like 17, 18 different machine learning models. And when you see this red here, that's when what clinicians call retrospective testing. So you can't just develop a model and just put it on patients. So there's a process where you first test on past year's data. And you can have a lot of issues like COVID, for example. It's a new thing that machine learning wasn't used to. And also there's another process called observational trial. So once you pass the retrospective testing, and if you're good, if your model is, it's reasonably good, you go to the next phase wherein you actually have an observational trial, which could be across one center or multiple hospitals. And then you validate whether your model performs exactly the same as retrospective testing or if there are some problems to address. And then goes into the next phase, which is interventional trial. So now you've found out that there's, for example, if you've detected that there's a mortality risk or if there's a readmission risk, that's when you actually see on how you would intervene to change the outcome to the better. So, and it's a set of processes. But for now, what we'll focus on is 3 different models. So the first model is medical record linkage, which is when a person goes to emergency. So they're not in a position to say their name, or maybe there's some error with the nurse entering their demographics right. Now that's one of the models. And we also look at traumatic brain injury, which is another machine learning model that's trained. And I'll also, if time permits, I'll show you a live demo of wearables. So the patient journey, this is just for a single patient journey that had perhaps a car accident. So once he gets admitted to ED, so there's the linkage model, which ascertains their identity, because we need this as we'll need to know what their morbidities are in the past, and also if they have any allergies. And the second model is readmission. So if the model thinks that there's a possibility of the person getting readmitted in the next 30 days, so care would be diverted. And there's also a model that predicts the triage. So traditionally, you would have this triaging nurse look at your symptoms and they assign you a priority. But nowadays, you would have triaging on the ambulance itself or on the helicopter. So, and all that is done by AI. And then you have mortality risk, which is like tells you whether this happens at various points in admission. And then for a traumatic brain injury patient, they get admitted to ICU. And then there's other machine learning models that get processed either on POSI or on other clouds. And they let the clinicians know of their risk to, say, a brain hypertension event, things like that. And that's just one of the patient journeys. It can have, there may be many of them. And the hard part here is if you have to give this data to researchers, it takes like a couple of months to years if it has to go through the formal process. Another way of getting access to this data is through either synthetic data, where we have a machine learning model that generates statistically significant, and highly correlated data to and with privacy preservation mechanisms in place to the original cohort. And we also point them to open source data sets that have similar patterns as ones that we store in Department of Health. So this is what the medical data is. So it's the 3 V's that people usually talk about, but so it depends on the patient. So for like patient with a lot of MRIs or CT scans during their admission, or having time series data continuously being monitored, that produces a lot of volume and also high velocity. And you have a wide variety as well, because it's CT scans, MRIs, pathology reports, and then waveforms, and also free text, which is like the clinician notes. The challenges that we have with this kind of, with constructing any data pipeline that uses predictive elements is one of the main things that come with cloud is egress, because you're looking at waveforms continuously, and it's not just you, but a lot of clinicians. So that'll actually be very expensive to export any data out of the cloud. There are issues with Python as well, bottlenecks, because it's interpreter, and Python is not mature enough. And sometimes you would have to write that low-level code. There is also scalability, which is if you have 2,000 patients, how would you scale your infrastructure for on-demand predictions? You'll also need uptime and also privacy, which is you can't have your health data stored on any cloud. So there should be some mechanisms to protect privacy. There's also the issue of model versioning, which is like when you develop machine learning models, there's always a data drift or machine learning drift, model drift, and you have to retrain them. So, and CI/CD is continuous integration, which is when you change code, it has to be visible on the website immediately, or like when it's in deployment. So for a lot of this, supercomputer and as well as cloud hybrid solutions work to the best. Supercomputing in the sense we can save a lot of cost when we train or retrain models, and we don't have to pay for egress. And also the proximity to the hospital, just 8 kilometers, and that helps. So if you talk of our projects, we use low-level HPC routines where we kind of write Fortran code, or use something like JIT, which is just-in-time compilation, that goes along, piggybacks with Python. And also we use task parallel and embarrassingly parallel routines, wherein we use sections of HPC like for data generation or augmentation, wherein you synthesize data if there's lack of data, or you run several models in parallel with different parameters. And within a model, you could have multiple versions of the same model being trained on different kinds of data. And also you would have different model architectures So we use all different kinds of topologies in health data machine learning predictive workflows. I'd like to talk about record linkage. This is like when patient shows up, when you have only sparse information of the individual, like how would you ascertain their identity? So let's think of a autoencoder. This is a machine learning architecture that's used in a lot of deep fake kind of problems, wherein you throw an input data, like could be text, image, anything, but then it goes through several machine learning layers, produces the same output. Right? So you may be wondering, what am I doing here? Like, pass an input and you get the same output. But something that's important to note is, so as you keep going down the layers, the size of the data at each successive layer shrinks. So it starts with, say, a couple of letters. As you see, it goes down and then gradually goes up. So what you're doing is you're having a low dimensional representation of the original data set that you sent. And this is very informative in a way, because suppose I have like Charlie Chaplin here, right? I have an image of Charlie Chaplin and I pass this through something called an encoder and have a vector here. And now I have Laura and I have Hardy here, right? With a different set of numbers. So if I kind of train like a facial recognition algorithm and I look at how their vectors are aligned, so they are kind of aligned. So Charlie Chaplin vectors are together if you measure their Cartesian distance, and it's far away from, say, Hardy's. Okay. A similar thing happens with a patient getting admitted. So you have Charlie Chaplin, that's the unadulterated record. And once they show up at emergency, there could be QWERTY errors, name dispositions, or misformatted dates. But once you train a machine learning model in a way to use the maximum flop rate of an operation that's good for GPU, which in this case is like a DGEM or an SGEM. So you kind of formulate a problem wherein some vector that it throws out, and if you do a matrix multiplication across all different vectors, all right, O of n squared, you get the right match, cosine similarity. Or this is what is called same-ace network in machine learning jargon. But for this whole linkage, wherein you go right from encoding this into vectors and converting that to matrix multiplication, finding the links, you could code that up, because you don't get that natively on any machine learning framework. So you can code that up. And then you get similar matches. So when you have a high probability, and once you have your confidence interval set right, you get all the right identities associated with the individual, because it's trained to do that. And this is how linkage works. So traditionally, what they used to do is they used to still go for greedy searches, wherein it's still O of n squared, but they have fuzzy matching. One record searches with many. We're doing the same thing here, except that we're using the peak performance of a GPU. So originally, when it took 4 seconds to link a single record, imagine like patients showing up, hundreds of patients showing up across WA. You'll need to have this on-the-spot linkage, where you link the patient's identity with their driver's license, with their past admissions, morbidity, midwives, marriage, death, and births. And when we had a machine learning solution that linked almost like 18,000 records per second for a V100 GPU. And the nice thing about this is this preserves the privacy. because you just see a bunch of vectors and you can just throw a large, maybe 100 million by 32 kind of vectors times 1 times 32, right? So you get 18 million. And then once you reduce that to 2 or 3 links, and you get your links directly. And something to worry about here is what the size of your vector space, the output vector space is, because that can affect the performance, but not by much. Even when you change from DGEM to SGEM, there's not much of performance degradation. And this particular solution was used during COVID linkage because we didn't have enough linkers at that time, and people showing up at COVID clinics, and also during hotel quarantine. But putting this in production can be expensive because we don't have on-demand serverless GPU nodes. That's why you need to run your whole GPU cluster for a long time and in a live solution. In future, we also looking at extracting identifiable information from unstructured data sources, which can be biometrics like ECG, heart rate, a combination of this. If you have any questions, just pause and just let me know. Another algorithm that we designed, developed, and implemented in the last couple of years is what is called ICH prediction, which is intracranial hypertension prediction algorithm. This is for people with traumatic brain injury, when they have concussion, or like if they have a car accident. So their autoregulation suffers, and which is like the brain pressure suddenly spikes without giving enough notice for clinicians to attend. So when people with traumatic brain injury get admitted to ICU, so the doctors drill a small hole to insert a sensor to measure their brain pressure continuously. So what we did was we took all their data, which is sensors, pathology reports, CT scans, MRIs, and drugs, the medicinal drugs, and all that information, and pass that to a machine learning algorithm to actually predict if there is a risk of hypertension event. The problem with this is a cross-country trial. It's across Melbourne as well as Perth, and not everyone is willing to share data. So there's a thing in machine learning called federated learning, wherein you just share parameters around without actually sharing data. And also you should think about lean models, because some of these models, they run on bedside monitors and some of them run on ambulance. But how is that possible? But because this is a lot of data, you can't have machine learning models making sense of data of various forms. So what we do is we have a lean model at the bedside, which is, it takes all this at a single point in time and compresses that. Machine learning is used for compression. Again, something like a autoencoder is used. And we send that to POSI for processing. And there the data is uncompressed and then cleaned, and then passed through a set of predictive models. The predictions are then sent back to the clinician. They can see it from their phone. They're in a coffee shop, and then advise the nurse on what to do. And this is the architecture that we used, wherein AWS is used for dynamic load balancing. So for a lot of workflows, we use POSI, but when POSI has an outage, it automatically sends the data to the AWS stack. So it has streaming, which is based on message queuing, and also the ML stack. A lot of this is serverless, so there's no issue of scalability. And what happens is it's also mirrored with POSI. So POSI and AWS, they kind of mirror with each other. And there's also drift monitors in place, wherein if the models are kind of error or if there's problems with data, fires a retraining job on another cluster, which is Topaz. This was done several years back. And then the model repo is updated and the latest model is faces the user. So the data preparation step itself involves cleaning, which is like you remove outliers from the waveforms, and also the points in time wherein the patient is taken for an MRI or CT and there's not much data in between. And then you use a machine learning model to fill in gaps with that data, because the way you train these models is you hide part of the data and you ask the machine learning to predict the hidden part. And there's like 20 different models that are used for this project at different points in time. And there's also a model that kind of aligns the waveforms, because each waveform has a different clock. So the beat has to be aligned. And these are the models that are used. So compression is used at either an ambulance to kind of reduce the bandwidth of the waveforms to send to POSI. And also you have models for predicting whether a brain hypertension event is going to happen. And you see the gauge here. So it's based on the model complexity. Something to note is a less complicated model doesn't always take less time. So in something like LSTM, though there's not as many parameters, just because of the recursive nature and also the IO bottleneck. A transformer here, which is based on matrix multiplication, that does, even though it has like hundreds of millions of parameters, it predicts at a much higher accuracy, as well as the time taken is pretty low. The flops are pretty high. So the best model that we have is of transformers. The same thing that you use in writing. In writing essays, in like question answering and all that. So survival analysis is also used. This is the model part, but also the way you predict is the prediction mechanism also should be resilient to missing data. So you don't always impute that if there is a lot of missing data, because the confidence intervals on imputation is pretty low. So you have to have a framework wherein you use where you use patient's data with a lot of missing blocks, and then you train the model to predict a hypertension event. And it should be resilient to like patients suddenly dropping out of the trial, or maybe moving to another hospital where there's no monitoring available. So as I told you initially that when we looked at so there's something called explainability, which is there's a way to look at why the model is doing what it's doing. So initially when people were drilling a hole and to insert a ICP sensor, we thought that it's all around ICP that would matter in predictions. But to our surprise, we realized that it was looking at ECG waveforms, which meant that maybe we wouldn't need an invasive sensor. So it makes like 16 different sensors are passed to this model, but it was actually looking at ECG at different points in time, and which is the beauty of ML, because it does these spatiotemporal correlations, which is not perceivable to a human eye. So the clinicians get real-time feedback from Power BI dashboards, as well as the live web feed. There's one improvement on this in terms of architecture. There's also something called a Redis cache. Cache is because you would be hitting the message queue very often, like a lot often than then you would throw data at it, like for recording. So Redis helps with looking at what was last updated, and then we get the predictions on the web or on the dashboards right away. This is a typical timeline for the project. So the project was initiated in around March 2020. And we tried a lot of models, like all different kinds of models. And at one point, we kind of gave up because the accuracy wasn't becoming clinically significant. That's when we got data from Melbourne and Alfred, and the accuracy went up, and we productionized the code. So the future would be around predicting if a brain hypertension event occurs from X-ray or from ECG, so that you don't need the sensor. That's something that we'd be trying, as well as looking at CPP opt, which is cerebral perfusion pressure. This is like cerebral pressure is like a dial. They can control with medication. The problem with cerebral perfusion pressure is that it's not available for a long time. It's after the event happens that people get access to CPP opt, but we'd be also trying to use machine learning to predict CPP opt so that doctors can intervene ahead of the event. So once the patients get discharged from an ICP event, from an ICH event, we still monitor them. We still give them wearables, and we continuously monitor them. But what I'd be talking about is another project called CoHive, wherein we use wearables like Fitbit to monitor their risk of psychosis events in the community. So we give Fitbits to people in the community, and we stream their data, and we call them for screening if we see that there's a risk of psychosis. And a lot of this is driven by ML models. We also use ML for kind of reverse engineering, say the proprietary data from the wearable, because that's not streamed along. Let me just show you a demo first. If you can see here, this is like Fitbit data of an individual who's been monitored for the last 2 days. And we can actually see their alerts here. And some of these alerts are machine learning generated, and that's the battery as well as if they're wearing a watch or not. But you have heart rate, sleep, and activity. And based on this information, you can actually see if a patient is at a risk of a psychosis event. Because the nice thing about being in a hospital is you have wearable data as well as their past admission data. And we can make sense of both these data sets to see if there's a likelihood of an event. I think there's a question. Sorry, just looked at.
That's a compliment that your UI looks great.
Oh, thanks. So what we do is we just send a message to the user, and once they agree to the terms and all, the data gets streamed automatically. So 1 second. And that's the team that's involved in these projects. We have teams from Royal Melbourne as well as Alfred, as well as W Health. Yeah. Thanks for listening. And do you have any questions?
Thank you, Shiv. Really appreciate the presentation.